Okay, now I'm recording. Okay, I'm recording already. Okay, sorry, recording. Okay, so I already talked about degree of freedom. Okay, that means in degree of freedom is the ways where a gas molecule can store kinetic energy. Okay, and we talk about translational motion, rotational motion. You know, the gas particle can move left, right, up and down, translational motion, and gas molecule can also rotate. I show you different kind of rotation. It can rotate around the x-axis, it can rotate around the y-axis, it can also rotate around the z-axis. Okay, so I already show you about this. Yeah, vibrational motion is only above 1000 Kelvin. Okay, now I want to talk about this monoatomic, diatomic, and polyatomic. So what is all this? Yeah, why we want to talk about monoatomic, diatomic, and polyatomic? So monoatomic gas, like for example, like helium, neon, argon. These are inert gas. That means they only have one molecule. Maybe I straight away explain over here. Yeah. So we can imagine, monoatomic is like only one particle. Okay. Diatomic, like you have two particles. Polyatomic means you have like H2O, three particles like that. Okay. Or carbon dioxide, ammonia. Okay, so degree of freedom. Okay, translational motion. We know that all gas particle can move left, right, up, down, and forward, backward. Yeah. So let's consider, for example, like let's talk about monoatomic first. Monoatomic. So translational motion. So translational motion is like, for example, this gas particle, it can move. Of course, it can move. It can move in x direction. It can move in y direction. It can move in forward, backward. Yeah, can move left, right, up, down, and forward, backward. Isn't it? So they have 3 degrees of freedom. Yeah. X considered one degree of freedom, Y 1 degree of freedom, Z another degree of freedom. So all together you have 3. Okay, same goes to diatomic and polyatomic. Okay, so for example, like I just copy this. Same goes to all the others. Yeah, so no matter no matter it's monoatomic, diatomic, or polyatomic, they all can move, left, right, up, down, forward, backward. So all of them have 3 degrees of freedom, all of them. But for rotational motion, that's not the case. For monoatomic, it has 0 degree of freedom for rotational. For diatomic is 2. For polyatomic is 3. Why is it, class? Okay. Okay. I want to write down the formula first. For translational motion, we are talking about velocity v. Velocity v. So the kinetic energy is half mv square. Half mv square. But for rotational motion is omega. So the kinetic energy for rotational motion is half I omega square. Okay. So why is it monoatomic is 0 degree of freedom? That means in rotational motion, for monoatomic gas, you cannot store kinetic energy. Why? So it means that, you see, let me draw it again. Yeah, the x, y, and z. X, Y, and Z. Okay, for monoatomic class, for rotational motion, the formula is, the kinetic energy for rotational motion is half I omega square. So it's depending on the moment of inertia I. Yeah, it depends on moment of inertia I. Now, this for rotational motion, the X, Y, Z, all of them they are axis of rotation. Axis of rotation, isn't it, class? All of them are axis of rotation. Remember the video I show you? You saw my camera. I show you how the thing rotate along the x-axis as axis of rotation, y-axis and z-axis. So these x, y, z, they are axis of rotation. Okay, they are axis of rotation. So moment inertia. What is moment inertia? What's the formula of moment inertia? Total mr square. If you still remember about the rotation of rigid body. Okay. Moment inertia, if the mass is at axis of rotation, yeah, if like monoatomic gas, the mass is at the axis of rotation. Understand? Is at axis of rotation. So that means the R is 0. The R is 0. So moment inertia is 0. So for kinetic energy, rotational kinetic energy, half I omega square, the I is 0. So of course the rotational kinetic energy is 0. Understand or not? Maybe I show you my camera once again. Class. Let me show you my camera. Let me show you. Can you see? Can you see me? Class, can you see?
Yes, can see.
Yeah. So okay. So you see this is the x, y, z, they are axis of rotation. This mass can rotate around this axis. Okay, so moment inertia depend on the distance from the axis of rotation. If your distance is 0, that means your I is 0, moment inertia is 0. So kinetic energy is 0 also. You look at my camera. Yeah, you look at the camera. Yeah, this one. Okay. Okay, you see this one. Where is it? Okay. You see this one. Okay, this is the x-axis, isn't it, class? X-axis. Okay, right now let's say this is a monoatomic gas. So if the axis of rotation is over here, the mass is on axis of rotation. The mass is at axis of rotation. That means it rotate the rotational kinetic energy is negligible because it just rotate like this. It's either rotate this way, or rotate along the y-axis, or rotate along the z-axis. So the rotational kinetic energy is actually negligible because there is no moment of inertia. The distance is 0. Unless this particle is some distance away from axis of rotation, then only it has rotational kinetic energy. If the mass is on the axis of rotation, the rotational kinetic energy is negligible. To have rotational kinetic energy, the mass must to have rotational kinetic energy, yeah, the mass must be at certain distance away from axis of rotation. Then only they have considerable amount of rotational kinetic energy. If the mass itself is on the axis of rotation, negligible rotational kinetic energy. Understand, class? Understand? For example, okay, monoatomic on any axis. On any axis, it is negligible because the mass is on axis of rotation. You see, negligible rotational kinetic energy. Unless the mass is at certain distance away, then only it has considerable amount of rotational kinetic energy. This is the x-axis. So you must like this. The mass must be certain distance away from axis of rotation. Then only you have rotational kinetic energy, like that. Yeah. Or if y-axis like this, the mass cannot be over here. The mass cannot be over here. The mass must be certain distance away. Then only you have rotational kinetic energy. Understand? Or z-axis. Z-axis like this. I mean, the axis is facing you. My axis of rotation is facing you. Then the rotational kinetic energy must be like this. Understand? Must be like this. Do you see what I'm doing? Then only you have the mass must be certain distance away from axis of rotation. Then only you have significant. I can say significant rotational kinetic energy. So for monoatomic gas is only at the axis of rotation already. So no rotational kinetic energy whatsoever for any axis of rotation. Understand? If let's say diatomic, now I go for diatomic. The diatomic gas can be rotate like this. Can rotate like this. It can also rotate like this. It can rotate like this. But if on the x-axis, it rotate like this. So no rotational kinetic energy. Understand? For polyatomic, it can have all rotational kinetic energy for all axes. It can rotate because it can rotate like this. It can rotate like this. Yeah, it can rotate like this, or it can rotate like this. Do you see the difference, class? It can rotate like this. It can rotate like this. Which one I haven't do it? I can rotate like this also. You understand, class? Okay, back to my OneNote. Yeah, back to OneNote. Okay, so I want to unpin my camera. Okay, class. Okay, do you get the idea, class? Give me a thumbs up if you get the idea. Yeah. Okay. Good. So now can you see my screen? Can you see my screen? Can Okay. Now you see. So as I said, for monoatomic, the rotational motion is 0 degree of freedom. Okay, because the mass is at the axis. I can say mass. Sorry. So the mass. Hold on a second. What happened? Okay. Sorry. So this one, the mass at axis. The mass at axis. So no rotational kinetic energy. Yeah. Or we can say rotational kinetic energy is 0 lah. Yeah. Because the I is 0. The I is 0. Okay. But for let's say it's smaller. I want it smaller. Okay. Now let's say for rotational for monoatomic is 0. Okay. So what is the total degree of freedom for monoatomic? 3 plus 0 is just 3. Now for diatomic like hydrogen, oxygen, nitrogen. Why only have 2, not 3? So look at this. Yeah, look at this. I think you figure out already. Yeah, you figure out already. Yeah, I done the demonstration just now. I hope that you figure it out. Yeah, X, Y, Z. Let's say diatomic. I draw a diatomic molecule. Okay, you see, it rotates around, it has certain distance away. You see, these two atoms got certain distance away from y-axis. So for y-axis, got 1 degree of freedom. Got 1 degree of freedom. It can rotate around the y-axis. For z-axis, it also has certain distance away from axis of rotation. It also, these two atoms has certain distance away from z-axis. So it can also rotate around z-axis. Okay, that means it has a considerable or significant rotational kinetic energy for z-axis. For y-axis also, it has significant rotational kinetic energy. But for x-axis, no. For x-axis, why no? Because the mass is at the axis of rotation. For x-axis, the mass at x-axis. So the I is 0. So the rotational kinetic energy, which equal to half I omega square, is also 0. 0 joule. Understand, class? Because the mass, this mass is on the x-axis. So no distance. The r is 0. The r is 0, no distance. So the I also 0. So that means the rotational kinetic energy also 0 for x-axis. So how many degree of freedom? 1 and 2. For y-axis and z-axis only. So only have 2 for diatomic. So diatomic has 2 degree of freedom. So that means total 3 plus 2 is 5. So for diatomic, it has total 5 degree of freedom. Understand, class? Okay, everyone okay, Now, how about polyatomic? Of course, polyatomic, everything okay. Let me draw it out. Let me draw it out. Okay, let me draw it out. X, Y, Z. Okay, so let me draw it out. So that you see, polyatomic, everything okay. It can rotate around. You see, now the polyatomic, it has certain distance away from X, certain distance away from, like for these two atoms, certain distance away from Y. For Z-axis, also certain distance away from Z. So all axes of rotation got rotational kinetic energy. Can rotate around the X, can rotate around the Y, can rotate around the Z. So you have 1, 2, 3. You have 3 degree of freedom for polyatomic. Understand? Polyatomic. So total has 3 plus 3, 6 degree of freedom. Okay, everyone? Okay? For translational, all can move in all directions. So all of them have 3 lah. Yeah. Okay, good. So everyone, you understand already. Now, continue. You also saw this mysterious, what is the formula to calculate the energy for kinetic energy? This is the formula. 1 degree of freedom equal to half kT. This is the formula. So 1 degree of freedom is half kT. How to calculate the kinetic energy? What's the formula? Remember, 1 degree freedom equal to half kT. Okay, maybe I want to write it down. Okay, screenshot this one. Yeah, 1 degree of freedom is half kT. Okay, so let's put it over here. Yeah, this is the most important formula in today's lesson. Yeah, 1 degree of freedom is half kT. This is for 1 molecule, class. This is for 1 gas molecule. For 1 gas molecule, the formula to calculate this is the, that means this is the kinetic energy. Kinetic energy stored for 1 degree of freedom is half kT. It's not actually not equal lah. It's actually for 1 degree of freedom, the kinetic energy stored is half kT. Okay, in one gas molecule. Okay, half kT. What is K, class? K is called Boltzmann constant. K. Remember the earlier part I talked about K before. Very early part. Talk about K. K is called the Boltzmann constant. K is Boltzmann constant. 1.38 exponent negative 23. Boltzmann constant. Let's write it down. K is called Boltzmann. It's not spring constant. It's not force constant. It's not what? It's not thermal conductivity. They have same symbol but different meaning. Boltzmann constant. This is called Boltzmann constant. 1.38 exponent negative 23. That's and then negative 23 was the unit joule per coulomb. That's the Boltzmann. Joule per Kelvin. Is it? Yeah. So K is Boltzmann constant, and this temperature here must be in Kelvin. Yeah. So 1 degree of freedom is half kT. That's the formula. So now let's say monoatomic gas. How many energy for 1 molecule of monoatomic? So how to calculate, class? Very simple. Let me write it down. For X, Y, Z, each it has 3 degree of freedom. Yeah, it has 3 degree of freedom. That means 1 degree freedom, it has half kT amount of kinetic energy. So that means in x-axis, it store half kT of kinetic energy. In y-axis, it store half kT. In z-axis, it store another half kT of kinetic energy. And rotational motion, no kinetic energy because no degree of freedom, 0. So what is the total? Okay, let me write it down. Maybe I should write something over here. Okay, what is the, I should make the writing bigger so that you can see, everyone can see. So what is the kinetic energy for one monoatomic gas? Helium, one helium gas molecule. It's actually atom, isn't it? What's the kinetic energy for one? Yeah, what's the kinetic energy for only one atom? For only one atom, what's the total kinetic energy? So can you calculate for me? It is let me write it down. It is half kT multiply how many? Half kT multiply how many degree of freedom? How many degree of freedom?
3.
1, 2, 3. 3. That's right. So it is 3 over 2. 3 over 2 kT. That's right. That's it. That means that this is 3. Understand? This is 3. So easy, class. This is only for one atom lah. Remember, this is only for one atom. For helium, helium is monoatomic. 3 over 2 kT. You got the formula. You put in the temperature. You got the kinetic energy for one atom. For one helium atom. Now, how about let's modify the question. Let's say now I'm using oxygen or hydrogen. Let's say what is the kinetic energy for one oxygen? Oxygen is diatomic. Oxygen. This is not atom already. This is molecule already. Molecule. One oxygen. This is diatomic. What's the kinetic energy for one oxygen gas molecule? So is half kT multiply the degree of freedom. How many degree of freedom it has? See class. X has half kT. You know why everything is half kT, class? You know why everything is half kT? X got half kT, Y got half kT, Z got half kT, and then this one got Z got half kT, rotational motion, Y also got half kT. But why is it X no, because X no degree of freedom. So how many half kT over here? 1, 2, 3, 4, 5. 5. Total 5 for diatomic gas. So got 5, got times 5. So this is times 5. So it becomes 5 over 2 kT. So the kinetic energy for one oxygen gas molecule is 5 over 2 kT. Put in the temperature, you got the answer. In Kelvin lah, this one must be in Kelvin. Understand? Kelvin. Same question. Why everything is half kT? Why cannot be why this one put it 4 over 2 kT. This one half kT enough. Why must be all equal? It's all back to the principle of equipartition of energy. Where is it? Where is it? Principle of equipartition of energy. So equipartition, they all have same amount of energy. Each degree of freedom has same amount of energy. Why same amount of energy? Back to our assumption. Our assumption is what? Our assumption is all particles move randomly. They all move randomly in all direction, any speed. They don't move in just one direction. They don't just rotate in x-axis. Some of them rotate in y-axis, some of them rotate in z-axis, some of them rotate in x-axis. So they all rotate randomly. They move randomly in any direction. They also rotate randomly in any axis of rotation. So all of them half kT, equipartition of energy. Understand the class? Give me a thumbs up. Equipartition of energy. So all of them have equal amount of energy. You cannot say one partition has more energy than the other partition. No, each partition have equal amount of energy. Equipartition of energy. So all of them is half kT equally. So oxygen has 5O2 kT for one oxygen gas molecule. Now, how about I modify it? I want, let's say now, ammonia. Let's say now I want one ammonia gas molecule. So this is what kind of molecule? Polyatomic. This is poly already. Polyatomic. Polyatomic. So how to find kinetic energy for one gas polyatomic? How many degree of freedom it has? So it has 3 from rotational, 3 from translational, 3 from rotational. That means each of them have half kT. You know, X here got half kT, here Y got half kT, here also got half kT. It rotate around the x-axis also half kT, rotate around the y-axis also half kT, rotate around the z-axis also half kT. They all rotate randomly. Some of them rotate x-axis, some of them rotate y-axis, some of them rotate z-axis. They all rotate randomly, move randomly. So how many? 1, 2, 3, 4, 5, 6. Multiply 6. So you multiply 6. So the answer is 6 over 2 kT. Simplify, become what? 3 over 3 kT. That's the kinetic energy for one gas molecule. Understand, class? Now, class. Now I want to further develop. Yeah. I'm going to finish my lesson already. Yeah, just one moment. So now you have kinetic energy for one helium. Okay, for one gas molecule. Okay. So in short, what I want to say is what? What I want to say is the average kinetic energy for one gas molecule. Okay, you can see average kinetic energy for one gas molecule is better. Hold on a second. For in short, maybe I should just type it out. Yeah. Okay, so so average kinetic energy for one gas molecule, yeah, for one gas molecule is what's the formula, class? What's the formula is 1 over 2 FKT. That's the formula, class. For one gas molecule with F degree of freedom. What is the value of F? Depend. It depend. It is monoatomic or diatomic or polyatomic. Understand? For one gas molecule. Now, class, I want to modify the question even further. 102 FKT. Now, class, question. Let's say question. My question is, what is the average? Sometimes the question is average. Okay. Average translational. Average translational. Average translational kinetic energy for one gas molecule. What's the formula, class? If the word translational appears, that means it doesn't include the rotational kinetic energy. It doesn't include. And for any gas molecule, no matter is monoatomic, diatomic, or polyatomic, the translational is always 3, 3, 3. 3, 3, 3. Correct or not, class? So if the word is specified, if he is specified like that, translational only, that means the degree of freedom is only 3. So the answer is what? Tell me, class. It's 3 over 2 KT. Because F is 3. That means if specified like what is this? Excuse me. So if specified translational means the degree of freedom is fixed at 3 already. Okay. So the average translational kinetic energy for one gas molecule is 3 over 2 KT. Okay, if translational. Okay, now I want to further develop the question. Now this is where I expand. This is where I expand. Now, not let's say I want just the average kinetic energy for, let's say, 1 mole. 1 mole of gas molecule. Class, 1 mole of gas molecule. What do you think? So now, last time is only 1 gas molecule. Now you have 1 mole. Class, 1 mole. 1 mole is how many? 1 mole is how many molecule? Na, isn't it? Avogadro constant. That means how? I start from half KT. I start from my humble half KT. I start from my humble half KT. Be humble always. Yeah. I start from my humble half KT. That means this this, and then our gas molecule. Our gas molecule, I'm not sure it's diatomic or monoatomic or polyatomic. Never mind. Just treat it as mysterious F. It must have F degree of freedom. We don't know what value of F. Okay, so that means this one must multiply F, isn't it, class? And then 102 FKT is kinetic energy for only 1 gas molecule, isn't it? 1 gas molecule. Now, if you have 1 mole, you must multiply Avogadro constant, isn't it, class? I must multiply Na. This is what is Na, class? What is Na? I know it's Avogadro constant. Avogadro constant. Avogadro constant. That means Avogadro constant is number of molecules in 1 mole. Number of molecules. What is this? Yeah, number of molecules. Number of molecules in 1 mole of gas. In 1 mole of gas. Understand, class? That's why you multiply by Na. Because 102 FKT is only for 1 gas molecule. If you want to find 1 mole, you must multiply by the number of molecules in 1 mole. Understand, class? Understand? Give me a thumbs up. Good. Now, then you can simplify the formula. So what's the formula, class? It is 1 over 2 K N A F K T. See that, class? What is K and A? Remember what is K and A? From very early on, I did talk about K and A. What is K and A, class? Nah, K and A. K and A is R. R. Huh? K and A is R. So it become R. Wait. So that means this one, no. Okay. Okay. So K, and then NA go to the front. So FT. So this is, maybe I should write the other way, like that. So this is F, K, and A. Can you see, class? Multiply F, multiply NA. So you got K and A. What is K and A, class? R equal to K and A. So the formula become what? 1 over 2 F R T. 1 over 2 F R T. So this is the formula for 1 mole of gas. This is per mole. This is kinetic energy per mole already. Per mole. If KT 1 over 2 FKT, this is per molecule. If F 1 over 2 FRT, this one is per mole. Per mole. Okay. Now continue. Let's say I want to find the last one. Last one. Okay. Let me finish it. Let me finish the lesson for the last one. Just another, just 10 minutes lah. Just 10 minutes is done. Okay. What is the average kinetic energy for let's say N of gas? Just say of average kinetic energy of all gas molecules. Can you find what's the kinetic energy, average kinetic energy for all gas molecules? So how? Start from for our humble half kT. We know that gas molecule has F degree of freedom. We don't know how many degree, what kind of molecule. So multiply F, and then this is the kinetic energy for one gas molecule. Now, if you have all gas molecules, that means you have N molecules. You have total N molecules. So what do you do, class? Multiply N. Multiply N. Multiply N. This is remember, class? 1 over 2 FKT is kinetic energy for one gas molecule. If you have N molecules, you multiply N. So what's the formula? What's the formula, class? The formula is 1 over 2 F NKT. That's the formula. Average kinetic energy for all gas molecule 1 over 2 F NKT. Okay. If you have many molecules with N molecules, 1 over 2 F NKT. Remember what is NKT, class? What is NKT? What is NKT? Remember what is NKT? What is NKT? Pressure volume. So you can change it to, what can you change? You can change the formula. We can change the formula. PV is equal to NKT. And also, what? PV equal to NKT. PV also equal to nRT. That means NKT also equal to nRT. PV also equal to nRT. So the formula you can also change to 1 over 2 F PV, or you can change to 1 over 2 F and RT. Depend on if the question give you the N molecules. If the question give you the value of N, you use this formula 1 over 2 F and KT. If the question give you you have N moles of gas molecule, give you the in number of moles, you use nRT 1 over 2 F and RT. That's the formula. That's the formula. That's how you develop all the rows. Maybe some of you see it as confusing. You see, so many formula. Why? Yeah, what is this per molecule? 1 over 2 FKT. You don't understand. Now I make you understand already. You see, you have so many formula. You see that? Now, total translational. Why got NKT, got NRT? I already explained to you everything. Do you know that? Without you realizing it. I already explained everything to you. Never mind. Later we do question, you can understand even further. Okay. So these are the formula. This is the, see, average kinetic energy for one gas molecule is 1 over 2 FKT. Correct or not? 1 over 2 FKT, correct? Where is it? 1 over 2 FKT. Nah, see that? Average kinetic energy for one gas molecule is 1 over 2 FKT. Correct or not? 1 over 2 FKT. This is kinetic energy for one gas molecule only. Remember, one gas molecule. One gas molecule is 1 over 2 FKT. 1 over 2 FKT. If you have many molecules, not just one, if you have N molecules, let's say you have N, you have N molecules, what do? If you have N molecules, you multiply N, multiply N, then you got the total kinetic energy is 1 over 2 F NKT. Then you can further change it to PV, pressure, volume. If the question gives you in pressure and volume, you also can use this formula to find the kinetic energy of the whole gas. If the question gives you in number of moles, you just use 1 over 2 F and RT. Number of moles. See that? It's very flexible, flexible, versatile, you know. Okay, these are the thing, class. Now, the last one is this internal energy of gas. So what is internal energy of gas? It's the total of kinetic energy and potential energy of all gas molecule. So, but potential energy is negligible. Potential energy can be neglected because intermolecular forces can be negligible. Because we already make assumption. Still remember the assumption of kinetic energy we made before? The assumption? What is one over assumption? Now, our assumption, we assume that the intermolecular forces is negligible, except during the collision. So there is no interaction, attraction, or repulsion between atoms. Our assumption, we assume no intermolecular forces. No intermolecular forces. That's why potential energy is negligible. That's why potential energy is negligible. Where is it? Potential energy. This one. Intermolecular forces assumed to be negligible, so potential energy also can be neglected. So the internal energy of gas is simply the sum of all the kinetic energy. Okay, let me explain in the one note. Yeah, in the one note. You already learned this thing. This is the most important one. This one. Okay. How to find the this is the total. This is not average lah. This is the total. Total kinetic energy of all gas molecule. Yeah. How to find the total kinetic energy of all gas molecule? That's the formula 1 over 2 F NKT, or 1 over 2 F NRT, or 1 over 2 F PV. Okay. So now, talk about internal energy of gas. This is our last part, Our last part. Okay, let me just our last part. I don't want to drag you even more. What is the internal energy. Internal energy of gas. It is equal to understand? Simply it is just equal to total kinetic energy of all gas molecule. Yeah. In other words, I can say like this: internal energy of gas. The symbol is U. Symbol is U is actually equal to potential energy plus kinetic energy of gas. Yeah, potential energy of gas and kinetic energy of gas. But for potential energy is neglected because intermolecular forces negligible. So potential energy considered to be zero. Potential energy of gas considered to be zero. So the internal energy of gas is actually just equal to the internal energy of gas. So internal energy of gas is just equal to the total kinetic energy of gas. It's just equal to total kinetic energy of gas, which is this one. So the internal energy of gas, the formula of to find the internal energy of gas is 1 over 2 F and KT, or you also can write as 1 over 2 F PV, or you also can write as 1 over 2 F and RT. That's the formula. Okay. A molecule is 1 over 2 FKT, so you have n molecules. Yeah, in the ideal gas, you have many molecules, n molecules. Then the internal energy just simply multiply n. Because one molecule is 1 over 2 FKT. So multiply n, you get the internal energy of gas, which is what? The internal energy of gas is actually the total kinetic energy of all the gas molecules. In all gas molecules, it has n molecules. So that's why you multiply n. Or n molecules, or you can put as n moles. Give you number of moles, you just use nRT. Yeah, instead. Okay. This is the formula for internal energy of gas. See, 1 over 2 F nRT. So that's it, class. So if you heat up the gas, class, if you heat up the gas, the temperature increase. The kinetic energy of the gas will also increase. That means all the gas molecule move faster. The internal energy of gas will increase. The internal energy of gas will increase. The total kinetic energy of all gas molecule also increase. They move faster. They rotate faster. They move faster. They rotate faster. The internal energy of the gas also increase. So that's the formula, class. Later we're going to use this formula into in our problem solving. Okay, we finished already the first part of our chapter 9. Then I want to solve some problem. After that, we can continue with thermodynamics, the second part of chapter 9. Then we finish our whole syllabus. Okay, understand, class? Do you understand today's lesson? Give me a thumbs up if you do. Okay, thank you. If you don't understand, I recommend you re-watch the whole video lah. Yeah, I will post this video in the YouTube. Okay, thank you for today's joining, and see you. You need to prepare for your UPS 3 next week. Do your the objective question in the Google Classroom as soon as possible. UPS 3 is your final hope. It's your final hope. Please struggle for your admission for your university. Okay, thank you. Bye.
Yeah, thank you, sir.
Thank you,
Yeah.
sir.